In this video, let's start to get into some depth about where the shading reduction factors come from and how they're determined for a PHPP model. So let's dive in to where these shading reduction factors come from. It's actually a little bit complicated because the method of implementing shading has changed a bit over the years, but let's start at the very beginning with the most basic shading implementation that we can use when using the PHPP. So when using the PHPP, we are asked to input up to 6 data points for each window that describe its shading situation. We'll see we also have the ability to add in some additional shading reduction factors on top of that for a total of up to 9 individual data points for each window describing its detailed shading situation. But we start by describing the geometry of the shading situation of the window. We're asked to locate in space any potential horizon shading objects. So we look out from the position of the window out in space and we try and identify any neighbors, trees, horizon objects, lines of shrubs, fences, etc. that might cause some shading, some amount of shading. These horizon objects are objects that come up from the horizon. So rather than being overhang elements or something that comes down from above, these horizon shading objects are notable because they come up from below. So they're going to block off the lower portion, potentially the lower portion of the windows. And we're asked to see how far out and how tall those objects are. At the same time, we're asked to describe, well, where is the window in position relative to the wall? With our passive house buildings, we often build buildings that have very thick walls, very highly insulated thick walls, and those can often cause some amount of self-shading on the glazing, depending on where you mount the glazing. And so we're asked to input that information as well. And then lastly, any sort of overhang information is also described for the windows. It's very common to have things like roof eaves or direct overhangs, balconies, all sorts of elements that might be causing shading to our windows from above. So 3 different types of shading that we're asked to input when it comes to the geometry of any individual window. And this information is going to be used to calculate those shading factors. So to determine shading factors in the PHPP, the way it works is that we're going to enter all of this information on a window by window basis. And then the PHPP is going to take that information along with some things it knows about the windows because we've previously entered that information, go off and calculate a shading reduction factor for each window uniquely. So every single window in the PHPP gets its own shading reduction factor. In fact, it gets a wintertime shading factor and a summertime shading factor. The sun, of course, is going to be in a very different position in the sky in the wintertime versus the summertime. And so the way that the PHPP handles that is it calculates 2 shading factors, one for the wintertime period and one for the summertime period. Now, when it comes to the actual data entry and the actual method that we'll use when we get into the PHPP, of course, we'll see a lot more of that when we actually get into the PHPP together. We will take a look at this and model through all of this in some depth. But just to sort of preempt that a little bit and give you a primer for what you will see, is we have a series of rows very similar to our Windows worksheet. Each row in the table here corresponds to a different window object, a different individual window sash element. And you can see here that we have a series of columns, and the columns are going to allow us to put in dimensional information, sometimes in feet, sometimes in inches, for all of those geometric shading elements. And over on the right-hand side, we have the ability to put in winter and summer additional shading. We'll talk about what that is. And then lastly, we have the ability to put in temporary shading, things like blinds, lamellas, or roller blinds, etc. So an awful lot of data that we can input. Of course, we don't have to input all of this for every window. So if you don't have overhangs, if you don't have additional shading, it's not that you have to input every single value for every single window. But if you do have horizon obstruction objects, if you do have overhangs, if you do have additional shading elements, you have the opportunity to input them here. I should also note right up front that if you don't enter anything, if you don't input any data into this worksheet, by default, the PHPP is going to apply a 75% reduction factor to all of your windows. So that may or may not be a good value. It depends on your climate, where you are, the type of building. It may or may not be a conservative value. But if you don't do anything, the PHPP doesn't assume that there's no shading whatsoever. It just assumes that you haven't filled in the worksheet yet. And so it applies a 75% reduction factor for wintertime by default, unless you specifically put in a bunch of information here that describes your detailed situation. So let's walk through each of these in turn. We'll go shading 1, 2, 3, 4, 5, and we'll sort of talk about what all of those mean. So first of all, let's take shading type number 1, horizon objects. So these are objects, as I said, which are out in the field of view of the window. If you were to stand at the window and look out from the window, if you see an object in front of you, that would be considered a horizon shading object. So for our example building, what we'll see is that on the north side we have a garage, and that's going to cause some, or it will be interpreted as a horizon shading object. And the two data points that we need to enter for horizon data shading objects for every window is the dimension away, so measuring from the pane of glass out to the shading object, and then the dimension above, so measuring from the bottom of the glazing up to the highest point on that shading object. So we describe something of a triangle there. We're going to describe the base and the height of that shading point. The shading point there, going to be the highest point on whatever that shading obstruction object is. This could be a tree, it could be a shrub, it could be a fence, it could be a building, it could be a neighbor's house, etc., etc. So any type of object that comes up off the horizon, which is in the field of view of the window, will get interpreted as a horizon shading object. So there's two data points. Now we have two additional data points that we have to enter for each window, which describe essentially where the window is in plane with the wall. So as I said, it's very typical for these passive house buildings to have very thick walls. It's very, very typical for the windows to be mounted somewhere in the middle of the assembly, meaning that there's going to be some depth of wall that has the potential to self-shade or shade the window edges. And so in order to account for that and take into account the shading obstruction of the wall itself, the thickness of the wall, what we're asked to input for each window is how far back in space the glazing is. So measuring from the outer surface of the wall, so the outermost shading surface, in this case, not as we've talked about in previous lessons, when we sort of stopped the wall model back at the sheathing when we were assessing R value. In this case, we're not concerned with the thermal boundary. What we're concerned with is the physical boundary with the outermost shading object. So the outermost physical element that could cause some shading. We measure from that back to the glazing surface itself, the outermost pane of the glazing surface. And then we also have to input the left to right dimension in this case. So we're going to enter the dimension from the point, from the edge of the glazing, so the point where the frame and the glass intersect, measure from that point over to that outermost shading element. In this case, the exposed frame of the window, more or less. So two more data points describing the side reveal condition of the window. Now, that would be the case for a typical window, a sort of normal window, but what about if you have a asymmetrical situation? For instance, any type of mulled window will have a larger reveal on one side than the other. However, the PHPP only allows us to input a single value for the side reveal. And so the best we can do in the PHPP is to insert or calculate an average reveal. So in the case of our lift and slide glazing here for the operable unit on the left, if we were being asked to input the reveal dimensions, we would just take the average. So maybe we would have a reveal dimension of 5 inches on one side, but 70 inches on the other side. And so in that case, we would just take the average of those two values and input that into the PHPP. Again, the PHPP doesn't allow us to do a left and right. It expects us to input a single value for the side reveal of our windows, but it's not always the case that the side reveal is always the same. So we can just input the average value. So that makes sense if you have different side reveal, like horizontal dimensions, but what about if you have a difference in the depth of the wall itself? What if you have an asymmetry in the depth of the reveal shading? Well, that becomes a little more complicated. This is a plan view of the kind of situation I'm talking about. What if you had a window which was installed in a wall normally on the right hand side, but then maybe the wall juts out or turns a corner or something on the left hand side, or you have a fin, or you have a neighbor or something like that that you're up against on one side but not the other. Well, if, as in the case here, it's a south-facing window, the PHPP does have a solution for us. So if we look in the PHPP manual, what it tells us is that the way that we're supposed to handle a situation like this is that first we're supposed to calculate in this diagram what's noted as O reveal number 1. So first we would enter the depth or the geometry for O reveal number 1. We would calculate, or PHPP would calculate, the reduction factor for that reveal. Then we would copy that reduction factor. Maybe we would write it down on a piece of scratch paper, or we would take it off to the side. And we would enter that not as a reveal reduction factor, but as an additional shading factor. And then for the reveal, we would simply use the standard depth instead. So it's a sort of two-step process that the PHPP would recommend that we use for situations like this. First, we calculate the O reveal number 1 reveal shading factor, and then we enter that as an additional shading factor. We'll come and talk about additional shading factors in a few minutes, but we have the opportunity to enter additional factors if we want. And so what the PHPP says is take that into account as a special shading factor, and then just use your typical, your normal O reveal depth. However, what the PHPP manual does also say is that this method that I just described really only makes sense if you're talking about a north or south facing window. Something where there's a uniformity, a symmetry in the sun path around the window. And it says very straightforwardly, unfortunately, this approach that I just described can't really be generalized or applied to east and west facing windows. In those cases, only estimates will help. So you're on your own there. Not very helpful. But that's essentially what the PHPP manual tells us in these situations. So this method is better than nothing, but it's certainly recognized as not accurate when it comes to east and west conditions. So a couple different ways that we can enter the side reveal. And then the last shading type, or not the last, but the third type of shading was our overhang. The last of the geometry inputs is our overhang shading. So if we have some sort of a horizontal overhang, whether that's a discrete shading element, as kind of shown in the image here, or if it's something like a roof overhang, like the eave of a roof or a porch roof or something of that sort, in that case, we're going to enter two data points. We're going to measure from the surface of the glass out to the leading edge of that shading element. So that'll be our O over, that's the dimension of that overhang measured from the pane of glass. And then the dimension above. So we measure from the top edge of the glazing defined as the place where the glazing and the frame intersect. So the top exposed edge of the glazing, we measure from that point up to the bottom of the overhang itself. So again, describing something of a triangle there, we've got two data points describing the base and height of that shading element. And we're going to measure from that shading point down. So, as I said, up to 6 data points for the geometry of our shading objects. And of course, as we've kind of alluded to, there can be other more complex situations when it comes to things like asymmetries. Of course, these are not the only things that might shade our building or our window. And so the PHPP allows us the opportunity to put in what it calls other shading or additional shading reduction factors. And these additional reduction factors are going to compound on top of the geometry. And these are going to represent things like screens, or louvers, railings, any other elements. Anything else which is contributing to the shading of the glazing can be added in these segments. And often we can get quite complicated with the inputs that get put in here. These can be quite complex and they can take into account a whole variety of different situations. In all cases, they follow the same formula. 0%, very low values, would indicate fully shaded or a lot of shading, and 100% would indicate no shading whatsoever. So all of our shading factors are some number between 0 and 1, and 0 representing fully shaded, and 1 or 100% representing full shading, full complete shading of the glazing unit. If you do have questions about that, consult your certifier. There are lots of different situations that you might run into there. So do consult your certifier if you do have questions about any of that or any specific implementation of specific products. In addition to that additional shading, we are allowed to take into account temporary shading as well. Now, temporary shading is going to be things like roller blinds or shades, shutters, screens, any of those types of elements. Now, we're allowed to input those for all sorts of different objects. There is a table in the PHPP manual, which we have recreated here, with some typical shading reduction values for our to make things easier for you. Just to show you some different values that you might use for different types of shading or blinds. And maybe the one thing to call out here, or the one thing to note, is that the PHPP does insist on a difference between the effectiveness of exterior blinds versus interior blinds. And notice that the exterior blinds have a much lower shading factor, meaning that they're going to be much more strongly shading on the glazing itself. Those lower factors obviously indicate more shading. Whereas the interior shades, it's not that they don't help at all. They do help. They do some, but not nearly as much shading as exterior shades. We know that the interior shades are useful. So they're most useful psychologically, giving people a sort of lever to pull when they're overheated and they need some cooling. But they're not nearly as effective as exterior shades or exterior blinds, shutters, what have you, when it comes to actually blocking out the shading itself or blocking out the sun itself. So again, this table is from the PHPP. You can go to the PHPP and reference these values if you like. Or of course, you can get more detailed values from a specific manufacturer if you have some specific product in mind that you're looking to use. Now, you might be asking, well, what about trees? That's probably the other main shading element that we're asked to take into account. And unfortunately, I don't have a very satisfying answer for you. There is not, even today in 2021, when I'm recording this session, there is not a good method for taking into account trees in the PHPP. I know, it's very surprising, but there simply is not a good method for it. There is a method. It is not a good method. It is a very complicated and weird method for taking it to trees. If you want to try and implement that, I would refer you to the PHPP manual, section 18.4.2. They do have a sort of walkthrough for how they think you might try and capture the effect of trees in the PHPP. I don't like that method, not because I have a better method that I could offer, but because it's a very weird and very complicated method. But there is a method, but again, it's not a very good one. Well, so what might we use as an alternate? Well, I think probably as we move forward, we will need to start to look at more sophisticated shading methods and tools. The methods that I've been showing you so far, these numerical methods, are very good as far as they go. They're incredibly fast. They're, we think, pretty accurate in most cases. But I think that as we move forward, what we have to recognize is that there are a lot of probably better tools which are now available. These methods, this shading method that I just described to you, has been used in the PHPP for decades now. But there have been a lot of advances in computer technology and simulation technology over the last decades as well. And I think we're probably at the point where we need to start harnessing those and using those more advanced calculation methods when it comes to shading. Now, the PHPP manual does sort of recognize this. It says at the end of the shading section in section 18.4.6, it does recognize that, well, yes, absolutely, there are lots of other really good tools out there that you could use to calculate shading factors. Shading factors are very straightforward. You just calculate the radiation without any shading, calculate the radiation with shading, you can calculate a shading reduction factor. So we can use all sorts of really quite sophisticated and user-friendly software, which is available to us now to calculate these shading factors. However, the very last clause in the PHPP manual states very clearly it's not possible to use the results of a separate software to calculate shading factors for building certification. In this case, the standard shading algorithms of the PHPP are always to be used. Now, I don't like that at all. And I think that we should not accept that. I think that may have been maybe defensible 15 or 20 years ago. I don't think that makes any sense now in 2021. I think there are lots of very good, reliable tools that we could and probably should be implementing in order to allow us to calculate more accurate shading factors for the more complex and detailed situations that we commonly find ourselves in. So I don't think that we should accept that rule. I think we should push our certifiers to allow us to use more sophisticated, more in-depth, more detailed and nuanced methods for calculating shading factors. And in fact, we have had very good results having those conversations with our certifiers. And while this rule is clearly written into the PHPP manual, I think what you'll find in practice is that most folks don't adhere to it terribly strictly anymore. I think there's too many really good tools that we could use to get calculated shading factors. And so restricting us to being locked inside of Excel, I just don't think makes a lot of sense anymore. But that said, the way that we implement shading factors can be done using this numerical method. And for a simple building like the one we're doing in our example case here, it's not that crazy to use these numerical inputs. And so when we come back in the next series of videos, we'll turn our attention back to Excel and we'll get ourselves back into our example model and we'll start to actually fill in all of the values for our sample building and we'll see what kind of results we get using these numerical shading factor calculators. So I will see you back in the next series, and as I said, we'll turn our attention back to the actual modeling.